Hello, thanks for watching this presentation. I'm Arash Sheikhlar, and I'm presenting my team's research paper on causal generalization in autonomous learning controllers. Let's start talking about generalization. We know that nature consists of infinite possibilities if an autonomous agent tries to do different tasks and achieve goals, which might be completely different. So the agent must find ways to deal with this diversity. And it's not a sensible solution to increase the memory size to store more and more information about different tasks and different environments. So the best way to deal with this diversity is to learn models and try to generalize those models such that they can be transferred and used in similar situations. This is a process that we call generalization. And in this cartoon, you can see a robot that transfers what it learns during painting a cat to another similar task, which is painting a dog. Our research relies on two pillars, causation and constructivism. Causation has a long history which goes back to 460 BC to Democritus, but it had not been formalized until 20th century. One of the recent attempts of mathematizing causality was done by Judah Pearl, and Judah Pearl in his book states that each parent-child relationship in a causal network represents a stable and autonomous physical mechanism. This actually means that if an agent can discover those physical mechanisms, he can use them in variations of tasks. In other words, if you can find those causal mechanisms, you can transfer them in different scenarios of the same environment. So the causal knowledge is task independent. But the question would be how would an agent learn those causal models of the environment? Well, he has to do causal discovery and causal learning via a constructivist approach. And constructivist theory of Piaget states that the mind of humans actively develops its cognitive capabilities via a self-directed constructive process. This approach has a particular focus on autonomy, and it's of course a psychology theory which was then brought to AI. But let's see what is causation and why we need that. We want to achieve AGI, so that AGI must be able to take actions and predict the outcomes of those actions. And that's a critical aspect of intelligence. So the ability to learn and perform tasks properly needs the information about what leads to what, which is causation. And generalization requires task-independent knowledge representations. And this is also what causation can give us. The knowledge about what causes what could be completely irrelevant and independent of the goals of an agent. And therefore, having this knowledge can be used when the goals change, which is a very critical property that does not exist in correlational learners, such as reinforcement learners. A causal model in a dynamical environment can be written in the way the first equation is written here. In the first equation, X is a set of variables that describe a process. X0 is the initial condition of that process. And this equation means that if you know the initial conditions and the physical laws governing an environment, you can predict what will happen after t time steps in that environment. Now let's assume that there is an autonomous agent in that environment. then the first equation changes into the second one. And the second equation, in the second equation, the agent knows how its actions, which are represented by u vector, influence the process such that it can make correct predictions about the outcomes of his interventions. This model actually connects the body of the agent to the physical environment. So in fact, the second equation shows that the state of an object now is not only dependent on its initial condition, but also to the inputs of the agent. And these n terms are, in fact, the noises of observation. And the third equation is the incremental form of the second equation. And you can obtain one from the other one very simply. So those agent inputs or signals are actually a form of intervention that we call input interventions. And there are two categories of interventions: input interventions and structural interventions. And change in the initial conditions is also considered as input intervention, because these input interventions do not change the structure of a dynamical process. And that is why they're called input intervention. And an interesting fact about these type of interventions is that by applying them in a strategic way, you can identify the causal structure of an environment, and you can learn the causal model simultaneously. So there has to be an autonomous agent that does these strategic interventions by itself, autonomously. And this is where constructivism comes into play. Constructivist AI has multiple requirements. Here we are focused on three of them. First, causal models should be represented in a transparent way. Second, these causal knowledge representations must be formed in relation to time, and they need to be temporal. Third, feedback loops are essential for interaction with the environment. In fact, to apply strategic causal interventions, we need feedback control. And by feedback, the agent can observe how exactly the current state of a process changes by taking every single action. So feedback is not only useful for control, but also the control of a process, but also it's useful for learning the causal models of a dynamical environment. So we need a controller that applies proper interventions to discover the causal relationships between variables. It applies intervention and carefully observes the outcome of those interventions. There are two types of interventions, two types of input interventions. In the first one, you change the initial value of an observable like xj, while you keep everything else the same, including the input signal and initial conditions of the rest of the variables, rest of the observables. And then if there is a distribution change in any of the observables, like xi, we say that there exists a causal influence from xj on xi. If I want to say it in simple words, when you change the initial condition of an observable, the distribution of another observable changes if and only if there exists a causal relationship between those two observables. The second form of intervention, the second form of input intervention is that you keep the initial conditions of all observables the same while you change one of the input signals like uj. Then if there is a distribution change in any of the observables like xi, we say there exists a causal influence from uj on xi. And in simple words, again, when you change the input control trajectory, the distribution of an observable changes if and only if there's a causal relation between that input control and that control input and that observable. We have to take note that here the controller must steer the agent to initial conditions to start a causal discovery process. And for the causal input interventions, we have to have this assumption that the environment must have stable initial conditions so that the causal interventions give us correct results. So the agent must look for stable initial conditions in the observation space before starting its causal interventions. And these two definitions that I just introduced are definitions of causal influence in dynamical systems that have been presented before by other researchers, and you can use them to detect if there is a causal relation between two variables in a dynamical system or not. But what we need is a controller that actually learns a model, and we don't really need just an identification algorithm. So the novelty of our research is that we introduce an algorithm that not only automates this intervention process, but also it enables learning an invariant model. And this model is being updated in an online manner. This algorithm is online because it updates the model constantly while it gathers data. And it needs to discover the causal structure simultaneously. Also, the model class has to include time in it, such that the agent can make correct predictions about the state of observables at each point in time. And this algorithm must eventually converge to an invariant model of task environment, which implies physical properties of it. And that's what we call a causal model. So we train the agent over the different causal experiments through different initial conditions and through different input trajectories. And then we test that in D+1 experiment. But the question is, how does learning the causal model happen? Well, the first step is to learn a correlational model. So any traditional method that gives you correlations between variables is accepted. Then the algorithm removes non-direct cause correlations and updates the model constantly. And what we mean by non-direct cause are correlations that might have common cause, or they might be spurious correlations, and or they might be invert cause and effects. So those are the correlations that are being removed by our introduced algorithm. The proposed model class for causal relations is a linear discrete state space equation. Matrix A specifies the relation between observables, and matrix B specifies the relation between observables and control inputs or manipulables. And this representation is common in modern control theory, but in that field, control engineers find A and B matrices using system identification tools, which are black box modeling methods. And those models are completely correlational, and therefore they cannot be generalized. In any case, for causal discovery process, we need to start the causal, we need to start the interventioning by computing a correlational model, which can be done by motor babbling or giving semi-random inputs and estimating a correlational model through black box modeling methods. But that's just the first step. And that gives us some initial matrices of A and B in which all components are correlated, and therefore all matrix components are non-zero values. So we need to get rid of those non-direct cause correlations one by one and replace their related values with zero in A and B matrices, and update the model every time an intervention happens. But let's see an example to see how this removing process might be done. In this example, let's assume that we have an environment that has two observables and two manipulables, or two input variables. And let's also assume that x1 has no causal influence on x2. Then the relevant component in A, which is A21, has to be 0. So the causal model becomes something like this. Also, we assume that U1 and U2 only have causal influence on X2. So the representation will be, the representation of matrix B will be something like this. And as you can see, B11 and B21 have been removed and replaced by 0. Finally, this is the algorithm that is being used. It gets input-output data given an initial condition and estimates the parameters of a model class, of the model class that I just introduced, constantly. And those parameters are integrated as A and B matrices. After every intervention, the non-direct cause correlations are removed from A and B matrices, and new parameters for the model will be estimated afterwards, while getting new data. And for updating model in this way, we need gray box modeling methods by which the algorithm knows some parameters of the model that are 0, but it may not know the rest of the non-zero values, and therefore it needs to estimate and update those parameters constantly. And the gray box modeling method that we are using is nonlinear least squares with automatically chosen line search method. We have implemented this method and algorithm on 2 tasks. The first one is called Run Davis problem, in which there are 4 mobile robots on a two-dimensional plane. The robots have to meet at the same location on the XY plane using the learned causal model. In this experiment, the algorithm converged to an invariant causal model, and then we tested that in Rendezvous task. The equations of the robot are two simple linear discrete equations that relate velocities in XY plane as control inputs to positions as observable variables. And if we augment the equations of all four robots, we will have one single status space equation. So the causal matrices that the robots need to learn are actually identity matrices, which mean that the controller must remove the non-direct cause correlations that correlate completely irrelevant things, such as the position of robot 1 to position of robot 2. They're totally independent, and position of one robot doesn't really influence on the position of another robot. And the algorithm does so. The algorithm does remove these correlations. And here is the result of the controller solving the task when it is tested on a completely new situation and a new scenario where the initial locations of the robots are completely novel and have not been experienced before. And the causal discovery process and invariant model learning took around 10 to 20 iterations of the main loop, which becomes from 160 to 320 causal interventions. And of course, that depends on, for example, how far the initial conditions are from each other, which makes the algorithm gather more data every time it performs causal interventions. In our second experiment, the same obtained causal model is used for another task in which the purpose is to follow a predefined trajectory. The causal model is learned already in the first experiment, but its prediction capability is being tested in another task by only one single robot this time. The trajectory, which is a circular one, is a totally new experiment for the robot. So the input trajectory is also new. But as you can see, a causal model is more capable in dealing with novel inputs. So it can be generalized much better than a correlational model. Also, the goals of the tasks have changed. I mean, the goals of this task has changed in this experiment. But since the environment is the same, the model is still useful, which shows the task independence property of causal models. Finally, we conclude that the causal models can solve a well-known problem called covariate shift problem in machine learning. The models in machine learning are sensitive to novel inputs, and if the distribution of the inputs are new to the models, they might give wrong predictions. But the causal models and causality can solve this problem. In addition, the task and the goal independence of causal models is a great tool that can be a basis for other forms of generalization. And our future research is focused on investigating causal inference in nonlinear settings. And those nonlinearities could be constraints on the observation space, on control inputs, on goals, or on the way the transitions happen from one state to another. That was all. Thank you very much for listening. If you have any comments about this presentation, please let me know about it. I would be happy to talk about it more. Thanks again.